Thank you everyone for coming. Today I will talk about asymptotic packing of geometric graphs. This is John work with Daniel Cranston, my advisor, Jiaxi, and Alexandra. We also would like to thank Abdel Basit, Austin 8, Bernard Lidicki, and Shira Zerbi for helpful discussions on this problem in GRWC 2021. Okay, let me first introduce graph decomposition, which is a classic problem in graph theory. Let H be a graph and G be a smaller graph. We say H has a G decomposition if it decomposes into H disjoint copies of G. And for example, a C3 decomposition of Kn is a Steiner triple system. Here we give an example of a Steiner triple system of size 7, and it is also famously known as the Fano plane. And it is well known that a Steiner triple system exists if and only if n is equivalent to 1 or 3 modulo 6. And this graph decomposition problems for any fixed graph G are basically solved by Wilson, who have proved that if we have a fixed graph G and then Kn and n is large enough, then Kn has a G decomposition if and only if it satisfies the following divisibility conditions. The first condition is that the number of edges in G must divide n choose 2, which means the number of edges in Kn. And the second condition is that the GCD of G divides n minus 1. Here, the GCD of G means that the greatest common divisors of the degrees of vertices of G. It is not hard to see that these two conditions should be necessary conditions for Kn to have a G decomposition. And amazingly, Wilson showed that these are also sufficient when n is large enough. Okay, so this graph decomposition problems are basically solved, and it is the result are very deep, and we're not going to talk about them today. And instead, we will talk about a graph packing problems. Can be considered as an easier variant of this problem. A G packing of H is a set of H disjoint copies of G in H, and we let P of H and G to be the maximum size of a G packing of H. It is clearly P of H and G will be at most the number of edges of H over the number of edges of G. And we say a graph G is packable if it satisfies these equations. Let me explain what does it mean. Here, the numerator on left-hand side, that is this P of Kn and G times G of G. Basically, it means the number of edge being covered by this maximum G packing of Kn. And this denominator n choose 2 is just the number of edges in Kn. So basically, it means that G is packable if some G packing of Kn covers all but little o n square edges. What is GCD of G? The GCD of all the vertex degrees. Yes, you're right. Okay. Any further question? And please feel free to interrupt me at any time if you have any questions. Okay, let's continue. So basically, the graph decomposition asks, when does Kn has a complete, has a perfect G packing, and asymptotic packing problems ask, when does Kn has a has an almost perfect G packing. And it is not hard to see that under this definition, every graph G is packable by Wilson's theorem, because Wilson's theorem says if n is large enough and falls into some modulo classes, then it can be perfectly packed by G. So we can always ignore constant number of vertices and then pack the rest of the complete graphs. And by doing so, we are only ignoring some big O(n) number of edges. So it will still be almost perfect packing under our definition. Okay, so the asymptotic packing problems for abstract graph is also completely solved under this definition. So instead, we will consider a geometric variant of these packing problems. So let me first introduce what is geometric graph. A geometric graph G is a graph whose vertices are in general positions, which means no 3 points on a line in the Euclidean plane, and whose edges are closed line segments whose endpoints are vertices. So in other words, they are just straight line drawing of some abstract graph. And here we have some examples of geometric graph. And two geometric graphs are congruent to each other if one can be transformed into other by translation and or a rotation. So here, the first two examples, they are congruent to each other because they can obtain by each other by translation and rotation. And the third one is not, it's different in this sense. Okay, another notion, a geometric graph is plane if no two of its edges cross. So here, the first two examples, they are not plane because they form some crossing. And the third example is plane because no two of its edges cross. Okay, more definitions. For any planar graph G, abstract graph G, we let this P of G to denote the set of all plane geometric drawings of G. And further, we let P star of G denote the set of all plane geometric drawings of G with vertices in convex position. Okay, note that this P star of G is a subset of P of G. Now, if we let C4 to be a 4 cycle, and we look at these three examples above, then G1 is not in P of C4 because G1 is not plane. It has some crossing. And G2 is in P star of C4 because it is not only plane, but also convex. And G3 is in P of C4, but not in P star of C4 because it is plane, but its vertices are not in convex position. So it is not in P star of C4. Okay, now let H be a geometric graph and let this category G be a set of geometric graphs, all with the same number of edges, E of G. Then we say a G packing of H is a collection of edge disjoint subgraphs of H that are each congruent to some members of G. And similarly, we let P of H and G be the maximum size of a G packing in H. We let Dn be a sequence of geometric drawings of a complete graph. Then we say G asymptotically packs Dn if it satisfies these equations, which is similar as before. It basically means that there is a maximum G packing that covers all the little O(n) square edges of Dn. So basically, this notion means that no matter how you draw the complete graphs Kn on the plane, you can always find an almost perfect packing, an almost perfect G packing. Okay. And under this definition, we say G is geometric packable if any geometric drawing of the complete graphs can be asymptotically packed by G. Okay, which means that it can pack into any drawings of the complete graph. And here is our main result. Our first main result. It claims that if G is a planar Hamiltonian graph, then the plane drawings of G, the set of plane drawing of G, that is P of G, is not geometric packable unless G is one of C3, C4, theta 1, theta 2, theta 3, and theta 4. And here, this theta C3, C4 means 3 cycles and 4 cycles. And theta 1, theta 2, theta 3, theta 4 are graphs as shown in the figures below. And further, we show that P of G is geometric packable if G is one of the 3 cycle, the 4 cycle, and theta 1, which means C4 with the chord. Okay, so this leaves us with 3 open cases. So when G is any of theta 2, theta 3, and theta 4, the geometric packing problems for P of G remains open. And we conjecture that they are all geometric packable. And here is our second result. If G is planar Hamiltonian graph, then the packing problem for P star of G is completely solved. Basically, it is not geometric packable unless G is the triangle, and P star of C3 is geometric packable due to the existence of Steiner triple system. Okay, now let me show you the proof of part 1 of theorem 1. Let's recall theorem 1. The first, maybe it is the second part. Okay, the second part of theorem 1 is we claim that P of G is geometric packable if G is C3, C4, and theta 1. When G is C3, it is obvious because of the existence of Steiner triple system. Now, let me show you why it is geometric packable when G is C4 and theta 1. To prove that P of C4 is geometric packable, first, we let Dn to be arbitrary geometric drawing of complete graph Kn with vertices V1, V2 up to Vn. And without loss of generality, we assume that V1 is on the convex hull and V2 up to Vn are in clockwise order around V1 with edges V1, V2, V1, Vn on convex hull. We have a figures on left-hand side. You can see, yeah, V2 up to Vn, they are in clockwise order around V1. Okay, then we pick all the 4 cycles in the following forms. You don't need to read that. Look at the figures on left-hand side. It basically means that we pick all the 4 cycles that contains vertices V1 and V5, V1 and V5. And we can observe that V1 and V5, the straight line determined by V1 and V5, they partition the plane into 2 parts such that each part contains the same number of vertices. So we can pair these vertices up such that we can pick some C4 that they are edge disjoint. And by picking this C4, basically we covered almost all edges containing V1 or V5, except maybe 3 of them. Okay, then we add all of this C4 into our C4 packing, and then we delete V1 and V5 from Dn to get Dn minus 2. And then we do this recursively until there are at most 3 vertices left. So in the second round, we pick V2 and V6 and pick some 4 cycles that covered almost all edges containing them, and then delete these vertices. And then in the third round, we pick V3 and V4 and do the same thing. And in the end, we have at most 3 vertices left. And each time we delete vertices, we discard at most 3 uncovered edges. So our packing here will cover all but big O and edges of Dn. Okay, so this completes the proof that P of C4 is geometric packable. Now let me show you the proof that Y theta 1, P of theta 1 is geometric packable. Recall that theta 1 is C4 with a chord. Okay, this proof is a little bit more tricky. First, we begin with an arbitrary geometric drawing of Kn, and we let M to be the floor of N over 4. And the second step is there exist 2 straight lines partitioning the plane into 4 parts, P1, P2, P3, P4, and each containing at least M vertices. This is by some topology theorem called ham sandwich theorem. You can Google it if you're not familiar with it. And anyway, we can do this, and then we pick all the theta 1s with the following form, with an chord. Their chord is between the part P1 and P3. You don't bother to read those index. Let's look at left-hand side. If we fix, if we fix K to be equals 1, now let's assume K to be equals 1 and J equals 1, then we will get the following, the red theta 1 on the left-hand side. And now if we fix K and varies J, so this is J equals 1. And this is J equals 2. And this is J equals 3. So when K is fixed and J goes from 1 to M, this chord between part 1 and part 3, they form the matching, which means that they must be edge disjoint. And now if we also vary K, then it's not hard to see that all the edges between P1 and P3, P1 and P2, P2, P3, P3 and P4, P4 and P1, all these edges are covered by this edge disjoint theta 1. And okay, all but at most 3n. And the reason that we do this 2 straight line partitioning into 4 parts is that this guarantees that this theta 1 are plane. So that's why we do that. Okay, so now what remains to be covered are 3 complete subgraphs as shown on the left-hand side. One of them is induced by vertices in the union of P2 and P4, and the others by vertices in P1 and P3. And we can just cover them by induction. And more formally, we try to prove that we can cover all but f of n, which equals 2n times log 2 of n edges. And what we have proved is that for those edges we covered in step 1, we cover all of them, but at most 3n. And for this remaining cliques, by induction, we can cover all edges, but f of n over 2 and 2 times f of n over 4. So this is what we have shown. And due to the form of f of n, this sum above equals f of n. So this completes the induction proof. Okay, this is the second part of theorem 1. And now let me show you the proof, the first part of theorem 1, which is the not packable part. And to prove that, we will need to introduce the notions of convex geometric graph. A convex geometric graph is a geometric graph whose vertices are in strictly convex position. And for convex geometric graph, or CGG for short, we have some different idea about when are they to be the same. And here, 2 CGGs are convex isomorphic if some graph isomorphism between them preserve the cyclic order of all vertices. So here, the first 2 examples, they are the same. They are considered the same as CGG because there is some graph isomorphism between them that preserve the cyclic order. And the third one is not isomorphic to the first 2 because you cannot find such an isomorphism. Okay, and given CGGs G and H, a G packing of H is a collection of edge disjoint subgraphs of H that are convex isomorphic to G. And we let P of H and G to be the maximum size of a G packing in H. These are similar definitions as before. And a CGG is plane if no 2 of its edges cross. And similarly, we define what does it mean by convex packable. It means that it satisfies these equations, and basically it means that there exists an almost perfect packing of the convex drawing of the complete graph. Okay, and one very important properties for planar Hamiltonian graph is that there is at most one way to draw G as a plane CGG. The reason I say at most one way is because it is possible that you cannot draw it as a plane CGG. For example, if you can think about a complete graph on 4 vertices, K4. K4 is planar and Hamiltonian, but you cannot draw it as a plane CGG because it will always cross. And okay, and therefore, if P of G is geometric packable, then G as a plane CGG is convex packable. And okay, so this last sentence, in other words, we can say that if G as a plane CGG is not convex packable, then P of G is not geometric packable. And this is the main idea to prove the negative part of theorem 1. Okay, now we let CK denote the convex plane's K-cycle. And here is our third main results. We prove that all plane Hamiltonian CGGs are not convex packable, except for the 2 plane cycles C3 and C4 and the 4 CGGs theta 1, theta 2, theta 3, and theta 4. And they are all convex packable. So for CGGs, we completely determined all the all the plane Hamiltonian graphs, whether they are convex packable or not. Let me introduce more notions. For any pair X and Y in CG, in a CGG, the length of this pair, denoted by L of XY, is the length of the minimum XY path along the boundary of a convex hole. So as an example, in the CGG below, which is the convex drawing of K10, the length between X and Y is 3 because if you begin at X and walk clockwise, it takes 3 steps to go to Y. So its length is 3. And the length between X and Z is 4 because the shortest path around the convex hole is counterclockwise, and it takes you 4 steps from X to Z. Okay, and we observe that the edge length in the complete graph Kn ranges from 1 to the floor of n over 2. And for each edge length, there are n edges. There are n edges of n of them. Okay, so the average, maybe except for n over 2, except n over 2, there are n edge for each edge length. So what's important is that the average edge length in Kn is something like 1 plus little O1 times n over 4. And we will need to use this fact later. And now, before introducing the general lemma we used, let me first show you some easy example why some graph is not convex packable. The first example we look at is the convex C5. Now let me show you why it is not convex packable. The key is that the average edge length of a C5 in Kn is at most n over 5. So any C5 packing of Kn has average edge length at most n over 5. And we already know that in an almost, the average edge length of Kn is something like 1 plus little O1 n over 4. So in an almost perfect C5 packing, it will cover almost all edges. So the average edge length will be at least 1 minus little over n over 4. Okay, so this average edge length is at most n over 5 and at the same time at least n over 4. So 1 over 5 less than 1 over 4 will imply a contradiction. Therefore, C5 is not convex packable. And to slightly generalize this argument, let's look at, now let me show you how we generalize the previous argument to show that C5 plus an edge is also not convex packable. First, for any, let's call this graph C5 plus. And for any C5 plus packing of Kn, if we consider the set of edges of all the outer C5, they cover edges of average length at most n over 5. And now we assume that there is an almost perfect C5 packing. If there is an almost perfect C5 plus packing, then the edges in the outer C5 will cover about 5/6 portion of almost all edges in Kn. We suppose these edges are the shortest 5/6 portion of almost all edges of Kn, then it contains almost all edges of length from 1 to n/2 times 5/6, because n/2 is the largest edge length. So it covers almost all edges of length from 1 to 5n/12, and hence it has average length at least 1 minus little o1 times 5n/24. So it is at the same time at most n/5 and at least 5n/24. But 1/5 is less than 5/24, so this implies a contradiction. And therefore, C5 plus is not convex packable. And now we try to generalize the proof that we just introduced into a more general lemma. And we need to introduce more notions. Let G be a CGG, and we say a set of edges of G is convex if for each edge, all other edges lie on the same side of the line determined by this edge. So for example, this set of blue edge is convex because for each edge, if we consider the straight line determined by that edge, we can see that all the other edges will lie on the same part determined by this straight line. But the set of red edges, it is not convex because the edges in the middle, if we consider the straight line determined by it, it will partition the plane into two parts, and each part will contain some red edge. Okay, and one important property of this convex set is that this convex set, if we consider them as some subgraphs in Kn, then their average, the sum of their edge lengths will be at most n. That's what's important. Okay, and here is the average length lemma. Let G be a CGG, and if G is convex packable, then there must exist some function f that maps each edge to some number that satisfies the following conditions. This function f, I want to stress that basically this function f means the average length of the set of edges covered by a certain edge. The normalized average length, the average length over n, which means the average length over n. Okay, and this function f, it must satisfy two conditions. First, for any set of edges S, the sum of f of E, well, for all the edges E in S is at least S squared over 4 times E. This first conditions, the intuition is that if we have a set of edges, then it must, and if there exists an almost perfect packing, then it must cover some positive portions of all the edges. And therefore, its average length should be at least something. This is the intuition. And the second condition is that for any convex set of edges A, the sum of f of E for all edge E in A is at most 1. This is because for a convex set of edges, the sum of their edge length is at most n, as I said before. And since this average length, they are normalized, so now it is at most 1. Okay, and using this lemma, we have this powerful proposition. Basically, this enough to prove that almost all planar Hamiltonian graphs are not convex packable. And this proposition say if G is a CGG and K is the maximum size of a convex set of G, and if the number of edges in G is less than K squared over 4, then G is not convex packable. Let's first prove it using our average length lemma. So the first step is we assume it is convex packable, and we let A be a convex set of edges of size K. Then by lemma 4, we are guaranteed some function f that satisfies the two conditions in lemma 4. And the first condition says it is at least K squared over 4 times U of G. And the second condition says it is at most 1. And if we simplify these inequalities, we have the number of edges of G is at most K squared over 4, and which is contradict to the condition. Okay, so this completes the proof. And now let's see how do we apply this proposition. Okay, first, if G is a plane Hamiltonian CGG, then it is formed by adding some number of chords to a plane cycle. And let's say number of chords is T and the length of cycle is K. And now if we suppose it is convex packable, then according to proposition 5, we know that if the cycle, the outer cycle is a C5, that is K equals 5, then the number of edges is at least 7. So which means that it has at least 2 chords. And when K equals 3, then by the proposition, we know that the number of edges is at least 9, which means that it has at least 3 chords. And when K is at least 7, we know that the number of edges, according to proposition 5, is strictly larger than 2K minus 3. But this will contradict the fact that G is planar. So imagine you have a cycle of length K, and you want to add chords in a planar way, then you can add at most 2K minus 3 edges. So if you have more than that edges, then you cannot be a planar graph. Okay, so based on this analysis, the only remaining candidates for a convex packable plane Hamiltonian CGGs are the plane cycles C3, C4, and C4 with a chord, which is theta 1, and C5 with 2 chords, which is theta 2, and C6 with 3 chords, which are theta 3, theta 4, and theta 5. Okay, now we have 7 candidates, and our theorem 1 say that we have only 6 possible. So in fact, we can show that theta 5 is also not convex packable by our average length lemma. And here is how we prove it. For convenience, I listed 2 conditions in the average length lemma here. And to prove that theta 5 is not convex packable, we partition the edges of theta 5 into 2 sets, the set of red edge and the set of blue edge. And we consider this sum, sum of f. Well, the first sum is go over edges in the red go over the red edges, and the second sum go over the blue edges. Now, by the first conditions, this sum is at least 81/36. This is because we can see the set of red edges and blue edges as one set. So if we combine them, they have 9 edges in total. So the size of S is now 9. So it is 9 squared over 4 times number of edges, which is 9. So it's 9 squared over 4 times 9. So it is 81/36. Now it is correct. Okay, and then on the right-hand side, if we look at the second conditions, the first sum is at most 1, and the second sum is also at most 1, so they're at most 2. So now we have 81/36 at most 2, which is a contradiction. And therefore, theta 5 is not convex packable. Okay, so far we finished the proof of theorem 1. And we don't have many times left. And let me summarize what our main results. If we let G to be a planar Hamiltonian graph, then P of G is not geometric packable unless G is one of 6 candidates. There's 3 cycle, 4 cycle, and theta 1, theta 2, theta 3, theta 4, as shown above. And further, we show that 3 in the 6 of them is geometric packable. So the geometric packing problems remain open for 3 cases, that is theta 2, theta 3, and theta 4. And if we consider P star of G, that is the set of convex plane drawing of G, then we know that it is not geometric packable unless G is C3. And further, P star of C3 is geometric packable. And if we look at this G, planar Hamiltonian graph G, as a CGG, then G is not convex packable unless G is one of these 6 candidates. And in fact, we can show that all of them are convex packable. And this is the evidence why we conjecture that they are also geometric packable. And for more details, you can find our papers on arXiv. Okay, thank you. These are all I want to talk today.
Thank you, Jiaxi, for the talk. And maybe we can all unmute ourselves and clap.
Any question? Okay.
Hagai sent a message in the chat.
Do all the edges have to be drawn in a straight line? Yes. Yes, we are only consider straight line drawing.
Okay. Yeah, and if you have any other questions, you can always message Jiaxi. His email is kind of in the CC of the announcement email if you want to reach out.